Hello friends, today we are going to see a topic from ring theory 2. Let's discuss about factorization of polynomials and reducibility tests. So before going to the topic, let us define what a reducible and irreducible polynomial is. See, we will first define what a reducible or a reducible polynomial is. We'll start with an integral domain. Suppose D is an integral domain and you have a polynomial f of x in the set d of x, and that polynomial f of x should neither be a zero polynomial or else a unit in dx, and then you call it an irreducible polynomial if whenever you write fx as gx into hx, where gx and hx are elements of your dx, where d is an integral domain, then gx or hx will become a unit in dx. That means it is not possible to write it as the product of two factors where neither of them will be a unit in dx. So now a non-zero non-unit element of dx which is not irreducible is known as a reducible polynomial in D. So coming back to the definition, you start with an integral domain and a function f of x which is non-zero and non-unit in dx, and if you are not able to write it as the factors, product of the factors hx and gx in such a way that neither of them is a unit in dx, then you call it irreducible, or else you call it a reducible polynomial. In the case that an integral domain is a field f, it is more convenient, although equivalent, to define a non-constant function in fx to be irreducible if fx cannot be expressed as the product of two polynomials of lower degree. So considering these examples, the first example that we are going to see here is 2x squared plus 4, which is irreducible over Q, whereas it is reducible over the set of integers Z. See, that is because the factorization 2 into x squared plus 2 is none of these is a unit in Zx. Now consider the next example, fx that is equal to x squared minus 2, which is irreducible in Q, whereas it is reducible polynomial in R. And another example that you have is fx is equal to x squared plus 1, which is irreducible in your Z3, whereas it is reducible in Z5. In general, it is a difficult problem to decide whether or not a particular polynomial is reducible over an integral domain, but there are special cases when it is easy. So our first theorem is a case in a point. See, it applies to the three preceding examples. So let us see the reducibility test for degree 2 and 3. Let f be a field, and if fx is a polynomial in the set f of x and the degree of fx is 2 or 3, then fx is reducible over f if and only if fx has a 0 in f. This is the first theorem which is going to be applied to the examples that we have explained earlier. How do we prove this? See, the proof is very simple. If you suppose that function fx can be written as gx into hx, so let us suppose that fx can be written as the product of gx and hx, where both gx and hx belong to capital Fx and have degrees less than that of fx. Since the degree of fx is equal to the degree of gx plus the degree of hx, and the degree of fx is 2 or 3, at least one of gx or hx has to be of degree 1. Now let us see the proof of this result. Suppose that we have the function fx, which can be written as the product gx into hx, where both gx and hx are elements of fx. Where f is a field. Okay. So here the degree of both gx and hx are less than the degree of fx, as we know. Since the degree of fx is the sum of the degrees of gx and hx, and we know that the degree of fx is either 2 or 3, so at least gx or hx should have degree 1. Now suppose gx is of degree 1 and let it be ax plus. So let us consider that gx is the polynomial with degree 1 and let gx is equal to ax plus b. Then clearly a inverse b is a 0 of gx and therefore it is a 0 of fx. So the first part is proved. Now coming to the converse part. Now for the converse part, suppose that we have f of a as 0. Okay. So if we have f of a 0, where a is an element of the field f, then by the factor theorem we know that x minus a is a factor of fx. And therefore we can conclude that fx is reducible over f. That is how the first theorem is proved. The theorem was like this: if you have a field f and fx is a polynomial in fx, then with degree 2 or 3, then fx is reducible over f if and only if fx is having a 0 in f. So we have proved it so easily, both the parts. So let us stop here and go to the next theorem.